a smooth family of time-like geodesics. And here they are. The geodesics are parameterized by the proper time of the astronauts, and the astronauts are labeled by a parameter S. We just have a one parameter family of astronauts that are just lined up like that. And so we have a geodesic in the S direction, and which is space-like, and a geodesic and all those geodesics in the time-like directions as well. We defined those vector fields eta that point from one astronaut to his or her neighbor, and the singularity theorem then claims that this is what happened in the past. This might be today. People are drifting apart from each other, and in the past, that eta vector shrunk. And eventually, we have a singularity over here. But how do we do that? I mean, so far, we've had mostly definitions. We need to get into the dynamics of things to be able to prove that really, if we can follow that back in time, maybe not analytically, not with an explicit solution, but maybe we can put some inequalities to it so that we can eventually conclude that there was a divergence. All right, so how does this eta vector that points from astronaut to astronaut, how does that evolve along a geodesic? Remember, here was this Ballet matrix. It said that if you covariantly differentiate the eta vector in the time direction, so the rate of change of eta as you follow along the geodesic is given by multiplying the eta vector with the Ballet matrix, which is this. And we decompose that matrix into three components. An antisymmetric component that describes a twist, dancing around each other. A symmetric component which describes a sphere, which is a sphere going into an ellipsoid, but while preserving the volume of the sphere. And a third term that doesn't actually turn a sphere into an ellipsoid. It will keep a sphere, but it makes it bigger or smaller. And that is the term that contains the expansion. Explicitly, the antisymmetric term was the antisymmetric part of the Ballet matrix. The symmetric volume-preserving term, the shear term, was the symmetric part, subtracting away the expansion, and the remainder is the expansion term. So the twist is turning a sphere into the same sphere but rotated. Everybody just rotates around each other. The shear is turning a sphere into an equal volume ellipsoid, and the expansion is turning the sphere into a larger sphere or a smaller sphere. And the definitions were that the expansion is given by the trace of the Ballet matrix, where the trace is defined as the contraction with the metric. And H was the projection operator onto the directions that are orthogonal to the time direction for the astronauts. We showed that the trace of B is the expansion, but the expansion can also be written as the projection of the Ballet matrix onto H mu nu. Now, what is the dynamics of the expansion? Here we need the Raychaudhuri or Raychaudhuri equation. We will use, for the derivation of this equation, the definition of the Ballet matrix, which was this, the covariant derivative of the tangent to the astronaut. And we will use that the curvature tensor obeys the Ricci equation. Remember, the Ricci equation says that if you covariantly differentiate a vector field twice, subtract what you get when you covariantly differentiate in the opposite sequence, then you get this expression in the Riemann curvature tensor, which is really saying that if you parallel transport a vector in a parallelogram one way or the other way, the difference between the two ways is given by a rotation that is expressed, that can be expressed in terms of the Riemann curvature tensor. And we also use that the vector field psi is tangent to the geodesics of the astronauts. So in particular, it's a vector field that is parallel to geodesics. So therefore, we have that the vector field psi obeys everywhere the geodesic equation. If we spell that out, this is the geodesic equation here again, just spelled out in terms of coefficient functions. Again, we can pull this factor in front, and we get this here, and these coefficients are just the psi b semicolon a. Since this is true for all basis vectors, we can also write the geodesic equation in this form: psi a, psi b, and then semicolon with a contracted is equal to 0. Okay, so we will use this definition, the Ricci equation, and the geodesic equation for psi. Now, let us calculate the rate of change of the Ballet matrix along the geodesics of our astronauts. Ultimately, we will only be interested in the trace, the dynamics of the trace. But let us start out with the dynamics of the entire B and then take the trace later on. Because, you see, we're only interested in the rate of change of the expansion, really. Okay, so we differentiate this tensor in the direction of the travel of the astronauts. So we calculate the covariant derivative of the B, the Ballet tensor, in the psi direction. That's this expression here. And by equation B, the Ricci equation, we can write this as this expression plus that expression. So we obtain that covariant derivative can also be written as these two terms. Now, what we have here is the covariant derivative in the psi direction. We can also write this term as the difference between these two terms. You see, here we are not differentiating the psi upper index c. Here we are. So I'm just bracketing in this way now. And you see, here it's the covariant derivative in the b direction of only this. Here, we're taking the covariant derivative in the b direction of the entire thing, which gives us an additional term, namely the one where we differentiate this. That we have to take away again. So this is what this term does. It's taking away the term where we covariantly differentiate the psi c in the b direction. So the sum of those two terms is this term. But this term here is vanishing by the geodesic equation. This is the geodesic equation. This is the covariant derivative of psi in the psi direction, because we're just contracting here. So that goes away, and we are just left with these two terms. So the covariant derivative of the Ballet matrix in the psi direction is given by these two terms. Here they are. Now, we use the definition of the Ballet matrix, and we identify this as a Ballet matrix, and that's a Ballet matrix, and there we go. This is just carried forward. So what we have overall is that we derived that the covariant derivative of the Ballet matrix along the tangents, along the flow of the astronauts is given by this expression here. We will then take the trace of this equation a little later, in order to obtain the rate of change of just the expansion of B. But for now, we've calculated the rate of change for all of B. So first, we now remember that psi is d by d tau, and the trace of B is the expansion that we are after. What that means is that the left-hand side is such that if we take the trace of it, then we just get d by d tau of theta. You see, if we take the trace of it, we get the theta, and the covariant derivative in the psi direction is d by d tau. So the left-hand side of this equation will turn into the time derivative of the expansion. That's what we need if we take the trace of it. Now, what does the right-hand side do if we take the trace of it? Well, let's take the right-hand side and express the B in terms of its three components: the twist, the shear, and the expansion. Okay, so the Belay matrix has a twist, which is rotations, a shear, and the expansion, and we need the square of the Belay matrix. So we get all those terms. And it's a little tedious, but you can convince yourself that only those underlined terms will survive. I mean, for example, if you have an antisymmetric contracted with a symmetric matrix, then that will be 0. Okay, so only those three terms will survive in that square of the Belay matrix. Then, when we take the trace of the right-hand side of our equation, we obtain that the trace of the square of the B matrix is, well, the trace of BB, which is those three terms here that survive. So it's an omega AB. This is a twist contracted with a twist, a shear contracted with a shear, and the expansion squared. Now, if we put all of these things together, we then obtain the trace of our equation. So remember, we had derived this equation here. We showed that the trace of the left-hand side is simply the time derivative of the expansion. On the right-hand side here, we have the square of a twist plus the square of a shear plus the square of an expansion. And we have this, and we have to take the trace of this as well. So let's take the trace of it now. And the equation, the resulting equation is called the Ray-Choudhury equation. Here it is. The derivative of the expansion is given by a term that has the expansion squared, the shear squared, the twist squared, and this. Now, that's positive, so this whole thing is negative. Same here. That's the square of something, so it's positive, it's negative. And that's the square as well, so that contributes negatively. So it would seem that, okay, so the expansion is actually diminishing, always. But there is this term, and this term might screw it up. It might be positive, it might be negative. What is it going to be? Now, if we knew what the sign of that term is, and especially if we knew that it was positive, so that it too contributes negatively on the right-hand side here, then we can start drawing conclusions. And we don't know, in principle, what the sign of it is. So at this point, we have to make an assumption. this is where the strong energy condition comes from. Let us assume that this expression here is always larger than 0 for all time-like xi. Remember that our xi is d by d tau is always time-like. Let us assume that that is so. Let us assume that this term is always positive. Now, at this point, we use the Einstein equation, which tells us that, remember, in 3 + 1 dimensions, the Einstein equation can also be written in this form. And therefore, the condition that this is a positive term, and therefore contributes with the same sign as the other terms, the condition that this is a positive term translates now into a condition on the energy momentum tensor. And that is the strong energy condition. So that's where it's ultimately having its origin. And remember that if we had a kind of matter that contributes strongly negatively to the pressure, then that can screw things up and violate that condition, which is actually what is nowadays expected to have happened, namely that in the very early universe we had an inflationary period that would violate the strong energy condition, and therefore we may not have had a Big Bang. And we may have that our universe was spawned by some sort of mother universe and so on instead. But in standard Big Bang cosmology, where we do not assume an inflationary early period, so the older standard model of cosmology, you could reasonably assume that the strong energy condition is fulfilled. And then, assuming the strong energy condition, we therefore obtain, if you look at the equation again, we therefore obtain that if this is a positive term, so with a negative sign, contributes negatively, we have that d theta by d tau is equal to minus a third theta squared minus some stuff, which is positive, minus some positive number. Which is to say that d theta by d tau is larger than minus a third theta squared. So in principle, it's very hard to actually calculate through that mess when the space-time has no symmetries and is evolving in a complicated fashion. But if we know that this is always positive, then we get at least an inequality. And the inequality is obtained by taking this term, that term, and just saying, well, okay, we drop that and make it an inequality. The inequality being this equation. So the strong energy condition gives us that d theta by d tau plus a third theta squared is more or equal to 0. And this would be the sum of the, twist terms, a twist squared and the shear squared and the term coming from the Ricci tensor. That equation we can reformulate now by dividing by minus theta squared. That will turn around the inequality, and we get a theta squared over here. And d by d tau of theta divided by theta squared can also be written in that way. So overall, we get a very simple inequality differential equation for the inverse of the expansion. Now, what we are after is a blowing up of the expansion, where theta goes to infinity. Now we're dealing with the variable inverse of theta. So now what we're looking for is a vanishing of that variable. Whenever theta inverse is vanishing, theta actually blows up to infinity, which indicates a singularity. So what then is the dynamics of theta inverse? Well, consider the cases where the geodesics are initially all either, let's say, diverging. So our astronauts are drifting apart from each other at the starting time, which means that all those thetas are larger than 0 at time tau naught, which might be the present day. This would be the case of an expanding universe. Or alternatively, we might look at the case where all those astronauts are starting to approach each other at the present time. That would be a contracting universe. This is a reformulation of the assumption that the extrinsic curvature is one way or the other. But we are doing this now locally in terms of the expansion. So let's plot the two cases. Here's a plot of theta inverse. Remember, we want to establish that theta inverse goes to 0 because that establishes that theta, the expansion, goes to infinity, establishes a divergence, establishes a singularity. So we are plotting theta inverse. We are interested in where theta inverse goes to 0. This is the time axis. This is the present day, tau naught. And let's say at the present day, theta inverse has a particular value. And our equation of motion for theta inverse is that the slope of the theta inverse curve is larger than a third. Okay, so theta inverse as a function of tau has a slope that's larger than a third. Let us plot the line with slope 1/3. This is the line whose slope is 1/3, as well as I could plot it. So what we know is that the actual curve, theta inverse of tau, here I'm plotting it, the actual curve theta inverse, if we follow that back in time, it must always have had a slope that's larger than a third. And you see this curve has a slope larger than a third. This would be more shallow than a third. This is a slope larger than a third. So we start at the present time, and we know that in the past, theta inverse followed a curve whose slope was always larger than a third. And that means that it stays below the line of 1/3, and that means that it must hit somewhere, it must hit the axis, which means that theta inverse must go to 0, and that indicates theta goes to infinity and therefore a singularity. So that is to say that we can use this theorem to conclude that if we have this expansion today, then in the past there must have been a singularity, a Big Bang singularity. On the other hand, we can also consider a universe which is shrinking. So let's say T naught is the present, is today. Again, the same inequality differential equation holds. And we know that the slope of the theta inverse of tau curve must be larger than a third. So we start here and we ask, what is the curve theta inverse of tau? Well, the slope has to be larger than the curve of 1/3, so it has to at some point go through that axis, and therefore there's going to be a singularity in the future. So a contracting universe would have to have a singularity in the future. Yeah?
That depends though on the value of theta inverse of tau 0. Like for example, in the first case, if that value was large enough, then that line would have been
Sorry, are you talking about A?
Yeah, I mean, what I'm saying works for both cases. So for example, in A, like if the value of the inverse of the curvature at of the expansion at tau 0 was large enough,
we'd always be able to reach the axis.
But you see, remember the point was this: at the time t0, theta inverse takes some value. Let's say here, and then I draw the line, right? So no matter where I start, I can everywhere just draw that line of a third, and I will end up being below that and hit the horizontal line somewhere.
But if that line is, has a larger y-axis-intercept, then you can have that curvature, that slope that's larger than 1/3, but still not touch the x-axis in the positive times.
There's no initial positive time in this diagram.
Yeah, no, there is no initial time. You see, let's put it this way. Yes, there could be a singularity before that, right? You're saying it could be that the universe only started here, right? But that proves our point that there was a singularity, right? So, you see what I mean? Either we derive that there was a singularity in this way, or alternatively, the singularity might have been earlier, right? I mean, see what I mean, right? We're basically proving that there was a start point to the time axis. Yeah. Okay. Right, so the conclusion is that our equation plus, which is this one, shows that theta inverse must go to 0, so therefore for sufficiently early tau, you have a big bang, or in the case of a shrinking universe, for sufficiently late tau, we would have a big crunch, a singularity in the future. Now this type of reasoning also leads to other cosmological singularity theorems. Some of them do not assume global hyperbolicity, and the conclusions are weaker. Here we prove that all of those geodesics will end up being truncated at a singularity, but you can get away with fewer assumptions, but then when you make fewer assumptions, you have weaker conclusions. For example, only the conclusion that there exists at least one incomplete time-like geodesic. But that's in principle enough. You've already proven that there's a singularity. So what have we then shown? Have we shown that, well, yes, singularity is unavoidable under certain reasonable conditions, such as the strong energy condition? Do we know everything about it then? It turns out no, because there can be very different kinds of singularities. And I'm not even talking about space-like or time-like or light-like singularities. Even just the usual light-like ones, time-like ones, can come in different shapes. In fact, in the shape of a pizza, in one case. Let me show you what I mean by that. So assume a set of symmetries of matter, and space-time has been chosen. Then an exact solution, or at least its asymptotic properties, have often been found. Remember, we went to this classification of symmetries in space-time, and for many of those cases, solutions are known, and even for those cases where these analytic solutions are not known, the asymptotics of those solutions is known. And that's what we need to approach the singularities. So then, what people have done is chosen a time-like congruence of geodesics, and then calculated explicitly not just the expansion, of which we know that it's going to explode, but also the twist and the shear. And then see what kind of dance is going on as you approach in a glorious final moment when the universe contracts. You know, all those astronauts might perform some wild dance. Okay, so in particular, we can then see how the expansion or contraction of the universe behaves dynamically when there's not so much symmetry. And basically, the funny things that can happen arise because the Ballet matrix has not just expansion in it, but also twist, which is to say those rotations, and also shear. And now the twist is very difficult to handle, but can be avoided by a suitable choice of your observers. If you make your astronauts start out with tangents that are orthogonal to your space-like hypersurface, then you avoid that twist. So it's the shear that matters then. And what does that mean? Let us recombine the symmetric parts of the Ballet tensor. We had decomposed it into a shear part and an expansion part, where the shear was keeping the volume the same, but was turning spheres into ellipsoids. And all of the expansion went into that extra term, the so-called expansion term. But for the purpose of seeing how a singularity might unfold, I mean, it's no longer about the existence of a singularity, but how it looks like the singularity, it makes sense to recombine the two into the sum of the shear and the expansion, so everything's symmetric. And when we diagonalize this operator, the theta mu nu operator, then we obtain now a matrix that has these space-like entries, and the trace is no longer forced to be 0. Remember, this has trace 0, and that has also trace, but the sum of the two terms is a tensor that doesn't have to have trace equals 0. Instead, it's just, this is the expansion in the one direction, that's the expansion in the two direction, that's the expansion in the three direction. And then we define the local Hubble expansion. So this is a tremendous refinement of the usual Hubble parameter, which is usually, the acceleration of the expansion, or the deceleration of the expansion. It's the rate of expansion of the universe globally in an FRW space-time. Now we look at it locally. At every point in space-time separately, we ask what the expansion is in each direction separately. So the HI are functions of space and time, and they give us the local expansions of geodesics in the I direction. And then if you sum up the three, you get the usual expansion term, and that we call the overall expansion. It's the overall local Hubble expansion, and that is the directional local Hubble expansion. So this is a very fine-grained analysis of the expansion or shrinkage of the universe. So having those expansion coefficients, those Hubble coefficients, we can then define local functions that play the role of the scale factor of the universe in an FL Friedmann, Lemaitre, Robertson, Walker space-time. Namely, remember that the Hubble parameter is just A dot over A. Now we introduce variables Li for each direction, locally everywhere in space-time. And so we have these local scale factors, and also overall local scale factors as functions of space and time. And the time derivative is defined here as the time derivative with respect to the local astronaut's wristwatch, which is the direction in the, I should call it psi, not u. It's the tangent field to the geodesics. So then let's ask, what happens to those expansion parameters, to those scale factors, as we approach a singularity? So either in a big crunch, or if we look back in the past after a Big Bang. How did the expansion unfold close to the singularity? The full set of cases is not known, but explicit examples have been found which have the following behavior. First, if we look at the usual Friedmann-Lemaitre spacetimes, then we have that all of the scale factors in each direction go to 0. In fact, they go to 0 at the same rate. Right? So if you go back in the past towards the Big Bang, you see that not only does the scale factor A of t go to 0, but also the local Li of t. All those local scale factors go to 0 at the same rate. But that's not how it has to be. And it's quite likely that if there was a Big Bang, that's not how it happened, because it wasn't completely symmetric. You can also have cigar singularities, where the scale factor goes to 0 in 2 directions, but in a third direction, it might even go to infinity. So you can have that the universe is sort of becoming spaghettified as you approach the singularity, either Big Crunch or Big Bang. If you either look at a Big Crunch in the future or Big Bang in the past, you can have that 2 dimensions, like the x and the y direction, might go to 0, but 1 direction blows up. That's like, a 3D structure becoming 1D. Spaghetti. A cigar singularity. You could also have that in 2 directions, the scale factors go to 0, but in a third direction, it's going to a constant. So that would be like a finite length spaghetti. A barrel singularity. Or we could have that the universe ends up in a pizza. Namely, you could have that the scale factors in 2 directions go to a constant. And in the third direction, it goes to 0. So it could be that the universe just pancakes. 2 dimensions just become completely squeezed together, and we end up with you see that in 2 spatial directions, it becomes of 0 thickness, and in that sense we have a singularity, but it still is a finite size pancake as its thickness approaches 0. That would be a pancake singularity.
Is there something that prevents the L1, L2 go to infinity, L3 goes to 0?
No, I don't think there is anything like that. I think anything is possible. It's just that for these we have evidence. Also, as far as I know, this is really unstable. We should not expect this. If there was a Big Bang, really, against all expectations, because the standard model is now no longer predicting a Big Bang. But if there was a Big Bang, then that is not what we should expect, or a Big Crunch. Except if there was something that really set the initial conditions to be very fine-tuned, so that all the dimensions started out at 0. But something like that, in principle, is more generic. It's much more likely that to have such a thing than that. Now, let me add a little bit about black holes and
some, if we didn't have extra dimensions in some of them, there's like a singularity in the past, and like their scale factor with a 0 and.
Yes, good question. And it could be that, in principle, it could be that our universe had more dimensions and lost some. Yeah. In fact, string theory would have it that this is basically what's happened, namely that the universe has 10 or 11 or 26 dimensions. String theory is the only theory that predicts the number of dimensions of space-time correctly up to an order of magnitude. And so, in any case, so yeah, 10 dimensions is usually what they go for. And of course, we don't see 10, we only see 3 plus 1. So the idea is that the remaining 6 are curled up very, very small. Now, there is a problem with curling up extra dimensions, because if the universe is expanding, how come that so cleanly 6 dimensions don't expand? How come that they stay as small as they are? Nobody really knows an answer to that. So in principle, all of this is possible, but we would expect a generic behavior, which would mean that some dimensions are large, some are small, but that some are very large and some others are extremely small. It's not clear how we can stabilize such a thing. Also, keep in mind that when you have small dimensions and you compactify them, that you have harmonic oscillators in those, and they have ground state energy. The size of extra dimensions for quantum mechanical reasons, basically for the reason of the Casimir effect, the volume, it doesn't want to stay the same. So there's, on one hand, there's the dynamics coming from GR, which, I mean, assuming that the Einstein equations carry forward to the higher dimensions. On the other hand, there's also the dynamics that comes from quantum effects. If you make something very small, then you're interfering with the uncertainty principle. The uncertainty principle will create a pressure, so to speak, that will want to make it big. Yeah. Yeah, the idea is that all of these issues will be resolved by quantum gravity. Yeah. Okay. Right. So this was about a singularity theorem for cosmology. Now, let me talk a little bit about the ingredients that go into singularity theorems for black holes. I won't actually go into the singularity theorems themselves, but there are some interesting concepts that go into them. Singularity theorems suitable for black holes involve, again, the expansion and contraction locally, but in particular, a concept derived from those, which is called a trapped surface. Now, what's a trapped surface? Consider here's the definition. Consider sigma to be a space-like hypersurface of space-time, preferably a Cauchy surface. So let's say sigma is a space-like hypersurface, three-dimensional therefore. Now, let's say that T is a subset of our space-like hypersurface, which is compact, it's two-dimensional, it's a smooth space-like submanifold of sigma. So sigma is a space-like hypersurface and T is a part of it. It's a two-dimensional part of it, I should say. It's a two-dimensional submanifold. What you should think of is, let's say, a sphere, an actual sphere, a two-dimensional sphere, for example, in space-time, at a particular point in time. So if you choose a particular point in time in space-time, that gives you a space-like hypersurface. Now choose, for example, a sphere, right? Compact, smooth, two-dimensional submanifold of our space-time. Now, consider the ingoing and the outgoing future-directed null geodesics that are orthogonal to that T. So we are having a subset of a space-like hypersurface, and we're looking at light rays that are going orthogonally to that surface. So let's say on that sphere, you have lots of people with flashlights, and they send flashlight, they emit light orthogonally to that surface, towards the outside or towards the inside. So we are looking at the ingoing and the outgoing future-directed null geodesics that are orthogonal to our two-dimensional smooth hypersurface, smooth space-like submanifold of the space-like hypersurface. You should think of those light rays as being just like our astronauts earlier. When we were talking about us as astronauts, and then at a certain time letting go of each other, and then we start floating, and the ballet matrix is telling how we are going to spin around each other, and expansion, contraction, and so on. We were assuming that we have mass. But you can do the same thing. You can also have a incongruence of geodesics that are light-like. So in this case, you're not letting loose astronauts who will then float in space-time and therefore trace out their world lines. No, instead you send out light rays, parallel light rays. And then you have null geodesics that form a congruence of geodesics. And you can also, for those light rays, calculate what the expansion is. In principle, what their shear is, and what their twist is. Okay, so let us look at something like a sphere, and we have light rays that emanate orthogonally from that sphere outside or to the inside. And we can ask, what about the expansion and contraction of such light rays? Now, if all these geodesics, the ingoing and the outgoing null geodesics that are orthogonal to the surface, possess negative expansion, then we say that T is a trapped surface. It's not going to happen for an ordinary sphere, right? Some geodesics will diverge, the outward ones, but the inward one will converge. However, all concentric spheres inside the Schwarzschild black hole are actually trapped surfaces. Now, how can that possibly be? Well, here is the Penrose diagram again of a black hole. Now, let me draw a spherical shell. It's nothing easier than drawing a spherical shell in a Penrose diagram of a black hole. You just draw a dot, right? Because if you draw a dot, then you're singling out, a point in R and T, and the actual sphere part of it is suppressed because there are two angles that describe where you are on the sphere, but the Penrose diagram doesn't show those angles. So you just pick a point, it's a sphere, right? Okay, so here, this is one of those spheres inside the horizon. So again, time goes up, space goes over here. That's space like infinity here. This is where the null geodesics end in the future. This is where they come from in the infinite past. This is the singularity at r equals 0. So here we have our two-dimensional space-like hypersurface, a sphere, and you can now send out light inwards or outwards. But if you send it inwards, it goes this way to the singularity. If you send it outwards, it goes that way to the singularity. It hits the singularity either way. And the expansion is actually negative in both cases. The light rays will contract in both cases. Now you may wonder, wait a moment, if I go this way, doesn't that mean that R increases? No, it doesn't. Remember that in the Schwarzschild metric, as you are going from outside the horizon to inside of the horizon, the signs in front of the dt squared and the dr squared flip, which means that r, the radial variable, becomes the time-like variable, and t becomes the space-like variable. So that's how it can happen that you have that, both are towards the singularity, both directions in the inward and the outward. Okay, so then we can define a trapped region. So a trapped surface is where the expansion is negative, both inwards and outwards. Now, if sigma is a space-like hypersurface, then the union of all trapped surfaces is called a trapped region. So in the case of a Schwarzschild black hole, every concentric sphere inside the horizon is a trapped surface. The union of all concentric spheres in a black hole is then a trapped region, which is basically all of the interior. The situation is more complicated in rotating black holes, but in the Schwarzschild black hole, it's simply like that. And then we can define the boundary of the trapped region. So that is the outermost trapped surface. Actually, it may not even be a trapped surface, because there, the boundary of it may be such that the expansion is negative only in one direction and the expansion is 0 in the other direction. That would be the boundary case. It would be called a marginally trapped surface then, because it's not actually that the expansion is negative in both directions. In one direction, it might only be 0. So the apparent horizon is, by definition, the boundary of the trapped region. Okay, so we have a trapped surface, meaning a two-dimensional surface towards the inside, towards the outside, null geodesics that are orthogonal, starting out orthogonal to the surface, will either expand or will all have a negative expansion. The union of all the trapped surfaces is the trapped region. The outermost of them, the boundary of the trapped region, is called the apparent horizon. And the apparent horizon then is just like any trapped surface. The apparent horizon is two-dimensional, space-like. Now, if all of this happened at one point in time, right? So at one point in time, we're choosing a space-like hypersurface. And then we ask, is there a trapped two-dimensional surface in there? And if there is, then we ask, how many are there? We take the union of them. And the union of them is the trapped region, and the boundary of it is the apparent horizon. Now, let's look at all times. So now we foliate space-time into space-like hypersurfaces. So we are not just dealing with one space-like hypersurface, sigma. We are foliating into space-like hypersurfaces, sigma with an index alpha, where alpha runs over the real line or an interval in the real line. It's like a time parameter, but generally not the time. And each of those space-like hypersurfaces will have an apparent horizon, right? So, or maybe not. But in any case, it can have an apparent horizon. For each one of those space-like hypersurfaces, you can ask for trapped surfaces, trapped regions, and the boundaries of the trapped regions. And the boundaries of the trapped regions are then the apparent horizons. And if you look at the union of all alpha of all the apparent horizons, now, so to speak, of all of the evolution of the universe, then that is a trapping horizon. Now, in the literature, there's a bit of a confusion out there. They don't all agree. Basically, some authors don't distinguish the apparent horizon from the trapping horizon. So the apparent horizon, strictly speaking, is for one foliation, for one space-like hypersurface. For one space-like hypersurface, you have trapped surfaces, trapped region, and the boundary of it is the apparent horizon. And then if you look at a foliation of space-time into space-like hypersurfaces, then for every space-like hypersurface, you have an apparent horizon, and the union of all of them, that's then the trapping horizon. Now, let me end with a few remarks. The trapping horizon for for Schwarzschild is the event horizon, but it's not always the case. Okay, I should go one after the other. So, why is it important to look at apparent horizons? Well, there's several reasons. Talking within general relativity, that is to say, without going to quantum field theory, where apparent horizons are important because it is thought that this is where Hawking radiation emanates from, not the event horizon, but the apparent horizon. No, let's just say within general relativity. Within general relativity, apparent horizons are a very useful concept because you can check for their existence now. Whereas for an event horizon's existence, you would need to know all of the future. Because remember that in order to define what the event horizon, how was the event horizon defined? You take the world line of an observer all the way to future infinity. And then you look at the causal past of that world line. And then the boundary of that is the event horizon for that observer. So you need actually to know all of the world line of that observer to know what the event horizon is. And if Hawking radiation came from an event horizon, it would mean that we could sort of predict the future, right? Because its existence depends on what happens in the future. And so if we saw already Hawking radiation today, it tells us something about, in principle, about the future. So the event horizon is a nice concept, but not very practical because it's teleological. You have to know everything about all the way up to future infinity. You have to know everything about the past, the causal past of future infinity. However, one can check for the existence of an apparent horizon in any space-like hypersurface. All you would have to do is calculate, or even better, go out there and measure the expansion of light-like geodesics that are orthogonal to the space-like hypersurface that you're considering. And then check, is it positive, is it negative? If it is negative in both directions, bang, you have an apparent horizon right now. You don't need to know the future for that. Now, for static Schwarzschild black holes, the event and apparent horizons coincide. And in particular, remember that the event horizon for a Schwarzschild black hole is light-like. It's at 45 degrees. And so is the apparent horizon then. But a black hole can grow, a black hole can shrink. I mean, in the actual universe, black holes grow because they always accumulate stuff, even if it's only the cosmic microwave background radiation. So it grows. And that means that the apparent horizon is actually, it would take a little too far to explain it in detail, but what it means is that the apparent horizon is actually space-like then. If the universe, on the other, not the universe, if a black hole, on the other hand, is shrinking because there's just nothing that it could absorb and it just radiates away stuff, then the black hole is shrinking, and that would mean that the apparent horizon is actually time-like instead of light-like. But either way, what one can prove is that for black holes in general, the apparent horizon is always on or inside the event horizon. It's never outside of the event horizon. Anyway, so these are the concepts that then go into the assumptions for singularity theorems for black holes. Okay, that's all I wanted to say today.